Another common form of potential energy is the energy from a spring. So let's say we have some mass m that's connected to a spring and it's at rest. So we call this position where it's at rest its equilibrium position. Okay, now let's say we were to stretch it so that now it's at some position x. Well, we all know how a spring works. If we let it go, it's going to bounce back and it's going to push all the way over to the left. It turns out it's going to go back a distance minus x, and then it's just going to oscillate back and forth, right? That's what a spring does. So what would the potential for something like this look like? The potential would be 1/2 k x minus x0 squared. Really, we should say the magnitude of x minus 0, so the difference between the two distances. Okay, and so we'll call the spring constant, we look at our units, and we know that potential has units of energy. We know that position has units of length, so the spring constant has units of energy divided by length squared. So we can see why, when after we've stretched it a distance x, why doesn't it just go back to the origin, right? Well, initially x minus x0 is 0, so we're setting our reference potential to be at this point when it's in equilibrium. When we stretch it all the way to the right now, the potential energy, so x minus x0 is just x. So this is 1/2 k x squared. The distance between these 2 points is also x. So our potential energy is 1/2 k x squared. So we have the same potential energy at both points at the opposite extremes, because minus x squared is just equal to x squared. So that means if we call this our initial energy, so our initial energy is when we stretch the spring, it's 1/2 k x squared. And then let's say we look at it when it's moved backwards, back to its equilibrium position. So our final energy, we have no potential energy, but we'll have some kinetic energy. It's the only other energy we could possibly have. So in other words, 1/2 k x squared is equal to 1/2 mass times velocity squared. So we have a velocity that's equal to the square root of k over m times x. So we see that we have some non-zero velocity at this point, and remember, that means the block is going to be moving to the left. Because when we're taking the square root, the velocity can actually be plus or minus this, and we know if we're calling this direction plus x, it's moving back this way. And so then we see that we have our initial energy now is 1/2 mv squared, and then our final energy, when it pushes all the way back to the left, is going to be 1/2 k, we'll call it x prime squared. So x prime is going to be the distance that it's moved back in that direction. But of course, we see that if we set these equal to each other, that x prime is just the same thing. The magnitude of x prime is the same thing as x. So it's going to go back to the left just as far as we had initially pushed it to the right. And so that's all we're really doing when we're solving a spring problem. So we're using conservation of energy just like we do for electricity problems and for gravitational problems. And so real quick, we'll go back and look at our answer here and check our units. And so we know that velocity should have units of of length over time. And let's see what we have here. So we have k, which has units of energy over length squared. So energy over length squared, so our units of k is mass divided by time squared, right? And then we're dividing this by, so if you look back to this formula, we have a k over m. So k over m is giving us units of, again, we have a mass on the bottom, so our masses cancel out, and so we see that because x has units of length, then v does have units of length over time. So our units check out, and we just need to make sure in this case that because velocity is a vector, we need to make sure that that we know that it's pointing to the left. So we need to make sure that we keep track of that.